deep into the sea made that journey yesterday to the bottom of the Pacific, a place known as the Mariana Trench's Challenger Deep.
In 2014, a $14 million deep-sea vehicle vanished near New Zealand's Kermadec Trench and was never recovered. But the bigger question wasn't just about the machine, it was why a space agency was building submarines in the first place. The answer leads to something discovered 13,000 feet below the Pacific Ocean that no one has been able to fully explain since. What do you think they actually found down there? Share your best guess in the comments. We're breaking it all down so you don't miss anything. From flagship to fleet. The loss of the Nereus was the kind of event that forces an entire field to reconsider its assumptions. The vehicle had been one of the most capable deep-sea exploration tools ever built, designed to reach the very bottom of the ocean at depths that crush conventional equipment. When it imploded under pressure near the Kermadec Trench, it took with it not just $14 million of hardware, but the logic of the approach it represented. Build one extraordinary machine, send it somewhere extraordinary, hope it comes back. Timothy Shank, a deep-sea biologist at Woods Hole Oceanographic Institution, looked at that loss and drew a different conclusion from the one that might seem obvious. The answer was not to build a better version of the same thing. The answer was to rethink the entire model.
We can go down to 6,500 meters, 7,000 meters with current existing technologies, submersibles. When you get below that, there's only like 2 vehicles in the world that can go down there.
The philosophy he borrowed came from the satellite industry. CubeSats are small, standardized, relatively inexpensive satellites that the space industry began deploying as an alternative to the single massive flagship missions that had dominated for decades. If one fails, you have not lost everything. If the design needs changing, you change it without discarding a billion-dollar investment. Multiple small vehicles sharing information produce a more complete picture than one large vehicle doing everything alone. Redundancy and distribution over singularity and scale. Shank brought that philosophy to the deep ocean and partnered with NASA to build a vehicle called Orpheus. Motorcycle-sized, roughly 550 pounds, built for under $200,000, which in the world of deep-sea research is a number that requires a moment to process. A second vehicle called Eurydice was built alongside it in 2018, both named after figures from Greek mythology whose story involves a descent into darkness and the question of whether anything comes back up. The buoyancy foam used in Orpheus had a previous life in James Cameron's 2012 deep-sea Challenger dive to the bottom of the Mariana Trench, material tested at the absolute limit of ocean depth, repurposed for a vehicle designed to go back down and stay longer. The heritage of the materials was appropriate for what Orpheus was being asked to do. The question of why NASA was involved at all had an answer that was considerably more interesting than institutional curiosity about the ocean. That answer was waiting in the outer solar system, orbiting Jupiter and Saturn, and it had everything to do with what Orpheus was about to find. The technology that connects ocean to space. Orpheus navigates without GPS. This is not a limitation unique to the deep ocean. GPS requires signals from satellites, and signals do not penetrate seawater. Below a few meters, any vehicle operating in the ocean is on its own, navigating by whatever internal systems it carries. At 13,000 feet with no tether, no remote joystick control from the surface, and no way to receive real-time corrections from a human operator, the vehicle has to be genuinely autonomous in a way that pushes the boundary of what autonomous means. The navigation system Orpheus uses is called visual inertial odometry, and it is the same system used by NASA's Perseverance rover on Mars. The rover cannot receive GPS signals either, for the obvious reason that there are no GPS satellites orbiting Mars. It navigates by continuously processing visual information from its cameras against data from its own motion sensors, building a running model of where it is relative to where it started and what the terrain around it looks like. Orpheus does exactly the same thing, except the terrain is the seafloor and the darkness is oceanic rather than Martian. The parallel is not coincidental. It is the reason NASA is building submarines. Multiple Orpheus vehicles are designed to share the three-dimensional maps they build of the seafloor, producing a collaborative picture of a region that a single vehicle could not assemble alone. The vehicles carry environmental DNA sensors that collect genetic material from organisms in the water column without physically capturing anything, identifying what lives in a location from the biological traces it leaves behind. Chemical sensors detect the signatures of hydrothermal vents and methane seeps before the vehicle is close enough to see them directly. In 2025, an Orpheus vehicle successfully mapped previously unexplored seafloor near the Mariana Trench at depths exceeding 5,600 meters, producing the first direct observations of polymetallic nodule fields in that region. The vehicle went somewhere no camera had been before and came back with a picture of it. The technology performed exactly as designed at depths that have claimed more capable and more expensive machines. The engineering challenges that Orpheus was built to handle, no GPS, total darkness, pressures that destroy conventional electronics, complete communication blackout from any human operator are not challenges unique to Earth's deep ocean. They are the exact challenges that any vehicle sent to explore the ocean of Europa, one of Jupiter's moons, would face. The deep ocean is not just a destination. It is a test environment for technology that has a much more distant destination in mind. Why NASA is building submarines. Europa is a moon approximately the size of Earth's own moon orbiting Jupiter beneath a shell of ice estimated at around 12 kilometers thick. Beneath that ice is a liquid ocean. The evidence for that ocean comes from multiple independent sources: magnetic field measurements, surface geology, gravitational analysis, and it is considered solid enough that the question is no longer whether the ocean exists, but what is in it. The pressure at the floor of Europa's ocean, estimated from what we know about the moon's size, the depth of the water, and the gravitational conditions, comes out approximately equal to the pressure conditions in Earth's Hadal Zone, the deepest ocean trenches below 6,000 meters. That equivalence is not a curiosity, it is a design specification. If you want to build a vehicle that can explore Europa's ocean floor, you need to test it at Hadal pressures first. The only place on Earth where Hadal pressures exist is in the deep ocean trenches that Orpheus is already exploring. Saturn's moon, Enceladus, presents a similar picture. Geysers erupting from its south pole have been directly sampled by the Cassini spacecraft, and the material in those geysers includes water, organic compounds, and molecular hydrogen, which is a chemical signature of the kind of water-rock interaction at hydrothermal vents that on Earth supports entire ecosystems without any input from sunlight. Enceladus is actively venting the chemical products of a process that on Earth produces life. That is a sentence worth reading twice. NASA astrobiologist Kevin Hand has stated directly that the discovery of microbial ecosystems thriving on chemosynthesis in Earth's deepest ocean serves as a guide for thinking about the potential habitability of Europa's ocean. The deep ocean is not an analogy for Europa. It is the closest physical approximation of Europa's conditions that humans can currently access and study in detail. The engineers working on deep ocean vehicles and the engineers working on Europa mission concepts are solving versions of the same problem. The deep ocean division of that work is happening now at depths that were largely unexplored a decade ago, with vehicles small enough and cheap enough to lose without losing everything. What they are learning has a destination that is not on this planet. Life without sunlight. In 1977, a research submersible exploring the Galapagos Rift descended to a hydrothermal vent and encountered something that forced a fundamental rewrite of biology. Until that moment, it had been taken for granted that all life on Earth ultimately depends on sunlight, either directly through photosynthesis or indirectly through food chains rooted in it. The idea was so deeply embedded that it was rarely questioned. Like the shape of the Earth, it was treated as an unquestioned premise rather than a hypothesis. The hydrothermal vent ecosystem overturned that assumption without warning. At fractures in the seafloor, superheated, mineral-rich water rises from beneath the Earth's crust and meets the near-freezing ocean. In these extreme conditions, total darkness, crushing pressure, and toxic chemistry, scientists found thriving communities of tube worms, crabs, fish, and vast colonies of bacteria. These organisms were not sustained by sunlight, instead they relied on chemosynthesis, a process in which bacteria convert chemical energy from compounds like hydrogen sulfide into usable energy. Entire ecosystems existed independently of the sun, powered solely by geology and chemistry. The implications were immediate and profound. If life could exist without sunlight on Earth, then the range of possible habitats for life, on Earth and beyond, expanded dramatically. Environments once considered sterile or hostile suddenly became plausible ecosystems. One striking example of extreme adaptation is the shrimp species Remicaris hibisi, found near deep hydrothermal vents in the Caribbean. These shrimp cluster along vent chimneys where temperatures can reach up to 750 degrees Fahrenheit, positioning themselves precisely at the narrow boundary where conditions remain survivable. Specialized organs allow them to detect heat, guiding them to these delicate thermal gradients. They host bacteria within their mouths and on their gill covers, effectively farming their own food. When bacterial populations are abundant, they feed on them directly. When resources become scarce, they shift their behavior, becoming predators and, in some cases, possibly cannibalistic. This flexibility reflects a highly specialized adaptation to one of the most extreme environments on Earth. Other deep-sea systems reveal equally unusual forms of life. The Champagne vent at northwest Ifuku volcano releases nearly pure liquid carbon dioxide, creating chemical conditions unlike almost anywhere else on the planet. Methane seeps along continental margins support communities of clams, mussels, tube worms, and eyeless worms that rely on methane-consuming bacteria. These environments are tied to vast reserves of methane hydrates, which may store a significant portion of Earth's carbon. In the Gulf of Mexico, dense brine pools form on the seafloor, lakes of hypersaline water so extreme that most organisms cannot survive within them. Yet life thrives at their edges, where chemical gradients create narrow zones of opportunity. These environments resemble conditions that may have existed on ancient Mars, offering clues to how life might arise elsewhere. Even more striking are discoveries beneath the Earth's surface. In 2006, microbes were found nearly 3 kilometers underground in South African gold mines, living in water isolated for millions of years. These organisms derive energy not from sunlight or organic matter, but from radioactive decay in surrounding rock. They exist in complete isolation, sustained entirely by geochemical processes. Across all these discoveries, a consistent pattern emerges. Life does not require sunlight, surface conditions, or a even connection to larger ecosystems. What it needs is far simpler: rock, water, and chemistry. These are not rare conditions. They are common throughout the universe. Astronauts on the ocean floor. 62 feet below the surface of the Atlantic Ocean in the Florida Keys, a habitat called Aquarius sits on the seafloor. It is the only permanent underwater research station in the world, and NASA uses it to prepare astronauts for conditions they will encounter in space. The NEMO program, NASA Extreme Environment Mission Operations, sends astronauts to live in Aquarius for extended periods to simulate the experience of living in a spacecraft. The ocean floor serves as a convincing analog for the surface of the Moon, Mars, and asteroids. Moving through water in a pressure suit approximates the resistance and physical demands of moving through a spacesuit in a low-gravity environment. The communication delays and isolation of working 60 feet underwater with no ability to simply walk back to the surface mirror the operational constraints of working on a planetary surface far from any rescue. The saturation diving that allows extended stays in Aquarius, where divers breathe compressed gas at ambient pressure until their tissues are fully saturated and can then work for days without the decompression penalty of repeated ascents, is itself a technology with parallels in the closed-loop life support systems that long-duration space missions require. The ocean floor has been doing double duty for NASA for decades, simultaneously as a research destination in its own right and as a proving ground for the human and technical systems needed to work in environments where the normal rules of surface life do not apply. The overlap between ocean exploration and space exploration is not metaphorical. It is operational, technical, and in the case of the Europa Mission Development Program, directly causal. What gets learned at 60 feet in the Florida Keys and at 13,000 feet in the Pacific feeds directly into the engineering decisions being made for missions that will not launch for another decade or more. The impossible finding: in 2021, researcher Andrew Sweetman returned to a remote region of the Pacific Ocean known as the Clarion-Clipperton Zone with a carefully designed experiment. His team placed sealed chambers on the seafloor to isolate small volumes of water just above the sediment. Within these controlled environments, they monitored chemical changes, specifically oxygen levels. Based on established deep-sea chemistry, the expectation was straightforward. Oxygen inside the chambers should gradually decline as it was consumed by biological and chemical processes. That outcome is considered fundamental. Instead, the oxygen levels rose. The increase was not minor, nor could it be dismissed as measurement error. Across 25 separate experiments, oxygen concentrations inside the sealed chambers climbed significantly, in some cases reaching up to 3 times the surrounding background level over a period of about 47 hours. The results were consistent within the experimental setup and completely at odds with existing scientific understanding of oxygen dynamics on the deep-sea floor. Sweetman's team began systematically testing possible explanations. Biological production was the first suspect, but it was ruled out by introducing mercury chloride into the chambers to eliminate microbial life. Even then, oxygen levels continued to rise. Other known sources were evaluated. Radioactive decay within the sediment, capable of generating small amounts of oxygen, accounted for less than 0.5% of the observed increase. Chemical reactions involving manganese oxides, another potential contributor, explained virtually nothing at the scale recorded. Each plausible explanation failed under scrutiny. What remained was a hypothesis with little precedent in ocean science. The seafloor in this region is covered with polymetallic nodules, small mineral-rich formations that accumulate over millions of years. Composed of layered deposits of manganese, nickel, cobalt, and copper, these nodules possess unusual electrochemical properties. Measurements indicated that their surfaces could generate electrical potentials of up to 0.95 volts. For comparison, splitting water into hydrogen and oxygen through electrolysis typically requires about 1.23 volts. While the nodules fell short of that threshold, certain catalytic processes, particularly those involving manganese-nickel oxides, can lower the energy required. Intriguingly, experiments showed that increasing the amount of nodule surface area within the chambers led to greater oxygen production, aligning with the idea that the nodules themselves might be driving the process. The findings were published in Nature Geoscience, prompting both excitement and skepticism. Critics, including researchers writing in Frontiers in Marine Science in 2025, questioned the experimental design. One alternative explanation suggested that tiny oxygen bubbles trapped in the equipment during deployment could have artificially inflated the readings. Others reported that similar measurements, conducted using remotely operated vehicles, showed only oxygen consumption. Some scientists argued that the proposed electrochemical mechanism was thermodynamically implausible under deep-sea conditions. As of early 2026, the results have not been independently replicated. Complicating the picture further, the study received partial funding from the Metals Company, a firm with commercial interests in mining these same nodules. While this does not invalidate the findings, it introduces an element of tension, given the potential economic implications. For now, the anomaly remains unresolved. The data is real. What it ultimately means is still an open question. The mining dilemma, the Clarion-Clipperton Zone, stretches 4,500 kilometers across the eastern Pacific. The nodule fields that cover its floor contain cobalt, nickel, copper, lithium, and manganese in concentrations that have attracted the attention of 16 firms currently holding active mining claims in the region. The metals locked in those nodules are critical components of the batteries that power electric vehicles, and the quantities involved are large enough to supply that market for decades. Half of the large animal species documented in the Clarion-Clipperton Zone live only on the nodules, not near the nodules, not in the sediment around the nodules, on the nodules themselves, on the surfaces of objects that grow at a rate of a few millimeters per million years, and that would require geological time to replace if removed. Mining those nodules does not just remove a mineral resource, it removes the habitat of organisms that exist nowhere else on Earth, in an environment so poorly understood that new species are still being identified on almost every dive. At least 32 member states have called for a moratorium or outright ban on deep-sea nodule mining, pending better understanding of the ecosystems it would affect. The scientific community studying the Clarion-Clipperton Zone has been consistent in arguing that the rate at which commercial interest in the nodules has developed significantly outpaces the rate at which the biology and chemistry of the region has been characterized. Mining a system you do not understand is a different kind of gamble than mining a system you do. If the dark oxygen finding is confirmed, the stakes of that gamble become considerably higher. The nodules would not simply be a habitat for surface-dwelling organisms, they would be an active oxygen source for the deep-sea ecosystem, a geological process supporting the chemistry that deep-sea life depends on. Removing them would not just destroy habitat, it would alter the chemistry of the environment that remains. The finding is contested, but the contest itself is an argument for caution, because the cost of being wrong in the direction of overmining is not recoverable on any human timescale. What it all means, every discovery from the deep ocean over the past 50 years has moved in the same direction. Hydrothermal vents showed that life does not need sunlight. Methane seeps showed that life does not need conventional food chains. Brine pools showed that life survives in chemical conditions that would kill most organisms instantly. Rock microbes in South African gold mines showed that life does not need any connection to the surface biosphere at all. The deep ocean has been systematically dismantling the list of things that life requires, and the list keeps getting shorter. What remains when everything optional is removed is rock, water, and chemistry. Those three things are not rare in the universe. They are present on Europa, they appear to be present on Enceladus, they may have been present on Mars for a significant portion of its history. Recent research from the Mariana Trench Environment and Ecology Research Project found biodiversity in the Hadal Zone to be extensive and flourishing despite conditions that nothing on the surface would survive. The deepest and most extreme ecosystems on Earth are not marginal environments supporting minimal life. They are diverse, active, and apparently robust. The tools built to study them are the ancestors of what will one day enter the ocean of Europa. Orpheus navigates the way the Europa lander will navigate. It operates without communication from the surface the way the Europa vehicle will operate. It endures pressures and temperatures and darkness that approximate the conditions any machine sent to an alien ocean will face. The Deep Ocean program is not a parallel to the space program. It is an early chapter of it. The most important question humanity has ever formulated is whether life exists beyond Earth. The deep ocean is not where that question gets answered. It is where the tools and knowledge needed to answer it get built and tested and refined. Every dive that reveals something unexpected about what life can tolerate on this planet adds a data point to the model of what might be possible elsewhere. The deeper the dive, the more unexpected the finding, the broader the model becomes. The ocean floor is a mirror aimed at the outer solar system. What it reflects back is stranger and more promising than anyone expected when the first submersible descended into the dark. A $14 million vehicle lost in the deep ocean. A motorcycle-sized replacement that navigates like a Mars rover. Blind shrimp farming bacteria on their own bodies. Oxygen appearing where no oxygen should be possible. Minerals that may be running chemistry on geological timescales. The deep ocean keeps producing findings that the frameworks built to explain it cannot fully contain. Subscribe so you never miss the next one.